Greetings, everyone. After many years, we are meeting face to face here, so feels good. We'll talk about PCIe 6.0 and also the journey beyond that, right? PCI Express is a multi-generational journey. We just completed the 6.0 specification, and what is in it for different applications. I will touch on that. Name is Devendra Das Sarma. We'll start with introduction, where I will talk about how PCI Express as a technology has evolved. Do a little deep dive into PCI Express 6.0. Also, I would have talked about 7.0. It will be very similar to 6.0, so pretty much you're going to get a preview of what it looks like. PCI Express technology and how it relates to storage, form factors, compliance, and then conclusions. So anytime you have a question, just raise your hand, shout the question, and I'll take it. Want to make it more informal. This is the evolution of PCI Express, right? We started off back in 2003 with 2.5 gig. At that time, it was 8-bit NB encoding. Pretty much on an average, right? Every 3 years, we have been doubling the bandwidth or the data rate with full backward compatibility. That's the average cadence. Sometimes it's a little longer, sometimes it's a little shorter, but on an average, give or take. And you can see that throughout this journey, it's like 2.5 gig, 2003, 5 gig, 2007, 8 gig, 2010, and note that 5 to 8, even though it's not doubling the data rate because of the encoding changes, you get double the bandwidth, which is basically what we wanted to do at that time, because if we went with 10 gig, we would have left the server channels behind at that time. So it took us a lot longer for the materials and everything to catch up. So after that, you will see that the progression keeps going. 16 gig was same 128, 130, 32 gig. If not, this would have been 10, 20, 40, and then 80, which would be getting harder and harder and harder, right? So you probably had to do PAM4 back in 40 rather than we basically wait till it's absolutely necessary for us to make a huge transition. So this is a big transition, and we'll see why. So it's a PCI Express, as we all know, has become the ubiquitous I/O across all platforms, right? That you can imagine anywhere. It's the interconnect that connects everything. And of late, you will see that alternate protocols like Compute Express Link, they are using PCI Express as the fundamental infrastructure. And it's one stack, one silicon that covers all the segments, but multiple form factors, as we will see. The promise of backwards compatibility is that you can take a by 16 Gen 5 device, it will interoperate with a by 1 Gen 1 device, right? Or vice versa, right? You can do any permutation, they will just interoperate. And this is not the end of the journey, clearly. We have, anytime we start such an undertaking, right? The general rule of thumb is 3 generations spanning a decade, very successful technology. By that means this is more than successful, right? In a good way. So more than 2 decades, now on to the 7th generation, pretty impressive, right? And the entire industry with 900 plus member companies that make up the PCI-SIG, they are behind the technology and lots of innovations happen. We announced the PCI Express 7.0 specification because, no prizes for guessing. After 64, it will be 128 gig. Okay, double, right? I mean, it's a very predictable cadence with which we move with full backward compatibility. It's going to be 128 gig, the same 1B flit mode as 64 gig, right? And, we make the transition once we make the transition, we'll take advantage of it for as long as we can. And 128 giga transfers per second, which means that you get 512 gigabytes per second per direction, right? For a by 16 link, we use the same PAM4 signaling. And of course, right now it's very early days. We think we can get there. Of course, like anything else, as you go through your, more and more details, things could change. But, the engineering judgment leading up to this is that this is feasible. Of course, we have a lot of hard work. By no means it's a slam dunk and all of that, but this is feasible, right? We are focusing on the channel parameters and the reach. The key would be to deliver the low latency and high reliability target, but most importantly, with the power efficiency and the cost effectiveness, right? And hundreds of lanes of PCI Express that exist in a platform. So this is the mix of the different data rate and the different width, and these are the bandwidth numbers that you get. And as I said, the promise of backward compatibility is that anything can interoperate with anything else. Of course, based on the least common denominator, right? You cannot have a by 2 connected to a by 16 and expect to get a by 16 performance. It will just give the by 2, but it will work. So what are the bandwidth drivers, right? What are the ones that are causing us to basically lead these speeds transitions, right? Speeds and feeds. On the device side, you got a lot of devices that are demanding high amount of bandwidth, right? So networking started off with 800 gig. That was basically that will be with PCI Gen 5 by 16. That becomes a networking solution. Gen 6, that is accelerators, FPGA, ASICs, memory, storage, alternate protocols like CXL. Once with CXL, you're providing the PCI Express so far had been a consumer of bandwidth, a good consumer, but nevertheless a consumer of bandwidth. And what I mean by that is, anytime you plug in a device, whether it is a networking device, it's a storage device, it consumes the memory bandwidth. And if you look into the platform today, the memory bandwidth is the bottleneck, right? A lot of the platforms, they have a lot of PCI Express lanes. You just cannot feed it because there is not enough memory bandwidth available. With the move of memory onto CXL, which is based on PCIe, it's now a producer of that bandwidth, which means that all the demand that you get, not only are you a consumer, but also you're a producer, which basically puts all the pressure in terms of having to deliver more bandwidth, because you're as the socket's compute capability is growing, and people are doing not just a single type of compute, they're doing heterogeneous compute, right? All kinds of computes are coming up. There is a need to deliver more memory bandwidth, more IO bandwidth. So it's the virtuous cycle of innovation that's going on, and the key to deliver all of this is power efficient bandwidth, right? And that's what basically there is a lot of requirement coming to PCI Express to deliver that. Now, while that's good and all of that, at the same time, you need to be cognizant of what makes this technology, or what has made this technology so successful up until now. And what has made the technology so successful up until now is that it's a cost-effective solution, right? If you think about something on the motherboard with hundreds of lanes, it's standard materials. It's not like exotic materials that you use. It's volume platforms, right? Shipping in billions of devices worldwide, right? So it's the volume platform. At the same time, performance has never been compromised, right? We are delivering performance. We are delivering the performance with the best power efficiency that the industry can expect. And of course, hundreds of lanes, right? Scalability is the other key thing, right? So with all of these, it's a tight rope to walk for the technology. And as I said, these are the new usage models, right? Storage, cloud, AI, analytics, edge, you name it, right? Everywhere it is there. PCI Express is there everywhere, whether it is as load store IO, or whether it is to deliver memory bandwidth, or what have you, right? I mean, it's there everywhere. With all of that demand for delivering the bandwidth within that same power, cost, and all of those envelope continues to be there. So, as I said earlier, I'll talk mostly about PCI Express 6.0, but also these are going to be the requirements, same requirements with 7.0, except the data rate will be double, right? Other than that, it's pretty much the same. In other words, none of these requirements, before we start, and this has been true for a while now, right? Before we start working on any technology, think of it as the guardrails that we put, saying these are the things that must be met. If you cannot meet, then of course you have to go back and have a discussion, but these are the guardrails, right? And none of these requirements are really, if you look deeply into it, none of them are really negotiable requirements. They all must be met. So data rate 64 gig, if we don't double the bandwidth, it's not worth the time for a lot of people to invest and go for a 10% frequency increase, right? It's a lot of heavy lift, so you have to take that step function. Latency wise, we don't want, because these are load store interconnect, right? These are not networking kind of interconnect. Every nanosecond of bandwidth matters for a lot of applications, right? Especially if you're doing memory access and things like that. Latency is important, super important. So what we said is that when we do PAM4, of course we knew that PAM4 means that the bit, as we will see in a minute, the bit error rate will be extremely high with all of that. We are going to do forward error correction, so that will increase latency. And what we said is that the latency adder should ideally be 0. If not, it has to be less than a single digit transmit plus receive, right? Those are the guardrails, right? And we clearly said that we cannot do the 100 plus nanosecond of FEC latency that networking standards have done. It doesn't work for us, okay? Because a lot of the load to use latencies, if you look at platforms today, those are less than that by themselves. So if you add 100 nanosecond on top of that, it's going to just become, you would not make the transition. You would stay in the 32 gig data rate. Bandwidth inefficiency. Another way of saying what's the bandwidth efficiency, both are the same thing. It has to be less than 2% adder. And by that what I mean is that if I was getting bandwidth X at 32 gig, when I go to 64 gig, I must get at least 1.98x. Okay. Reliability. Clearly, it's not a negotiable thing. We measure reliability in FIT, which is failure in time. How many failures are going to get in a billion hours? In a billion hours, that is, right? And we want it to be very close to 0. In reality, nothing is 0, right? There is always a probability of a failure happening, right? But we want that probability of failure in a by 16 link as measured in FIT to be as close to 0 as you can imagine. Channel reach, again, volume platforms, people don't change their platforms just because, you can't tell people that, hey, you are earlier in the motherboard, the PCIe, PCIe slots were 10, 12 inches away, now put them 2 inches away. It doesn't work, right? So you have to be, the channel reach has to be the pretty much similar to what it was there before. Power efficiency, again, better than 5.0. And you will notice that this is a soft requirement in the sense that ideally the power efficiency should be half of the prior generation power efficiency. In other words, if you spend 10 picojoule per bit with Gen 5, you should be spending 5 picojoule per bit when you are delivering 64 gig. So that way the power number will be flat. In reality, what happens is that initially when people come up with their implementations, the power numbers are higher, and then it takes a generation or two before they can tweak, and then it starts getting down, right? And in order to make up for that, we did a bunch of these low power enhancements, and we introduced a new low power state so that way you can modulate the link width and all. But that's the goal, right? Better, and of course, if your power efficiency is more than the previous generation, then it's clearly moving in the wrong direction. And other thing is plug and play, right? Full backward compatibility, again, something, you cannot really, it's not an easy thing to move away from, right? Because otherwise it causes a lot more issues and challenges. And of course, it has to be high volume manufacturing ready. It cannot be a niche kind of a technology, right? Very cost effective, scalable to hundreds of lanes in a platform. So these are the right trade-offs, and we had to meet each and every one of these metrics. So now, what's about PAM4 signaling at 64 gig? Well, unlike NRZ, which is non-return to 0, there are 3 eyes, not as 1 eye. And by that, what we mean is that we are keeping the unit interval the same as 32 gig. It's the same frequency if you want to think about it. Nyquist frequency is 32 gig, but instead of sending a 0 or a 1, we are sending 2 bits, right? That's why it is PAM4, full 4-level pulse modulation. And basically, what happens with that is because you are squeezing in, 3 eyes rather than 1, you're basically getting reduced eye height and also reduced eye width, and that increases the susceptibility to errors. You're much more susceptible for errors to happen, right? In other words, a small amount of voltage perturbation can move you from one to the other. So as a result, you will end up getting more and more errors, and that's fine. That's something that you cannot avoid. You just need to figure out how to work in spite of that. We did other things like gray coding to minimize the number of errors. These are well-known techniques. Pre-coding to minimize the number of errors in a burst, and all of those. And we'll talk some more about that. So given that we're getting a lot of errors so far, PCI Express had been the last 5 generations were all with a bit error rate of what is known as bit error rate of 10 to the power minus 12, which means that every 10 to the power 12 bits you can get 1 bit in error. Those numbers are, with PAM4, those numbers are many orders of magnitude worse, right? Just to give you an idea, when we started off, a lot of people said, hey, should we go with a 10 to the power minus 4? And I'll show you the numbers, some of the analysis that we did. Minus 4, like networking have done. So, bottom line, errors are several orders of magnitude worse than what we are used to. And we define, not only that, there are 2 other things that are at play here. In order to do lower latency, most people would most likely end up doing things like what we call a DFE, decision feedback equalizer, continuous linear time equalizer, those kind of designs, which means that an error that happens in a bit is most likely going to propagate to next few bits. Okay, because the bit, the way you determine what this bit is dependent on what the values of the previous few bits were. So they tend to propagate, right, with those kind of implementation. So that's what is known as a burst error. And you will see here that we define something called a first error. What is the probability of a first error happening? And then you're going to get a burst. And not only that, we are also cognizant of the fact that there can be some common events that will lead to a correlation across lanes, right? And those are the types of errors that we need to be careful about. So when we give a number, it's based on the FBER. The actual number of errors will be more than that. All of these errors count as a single incidence of an FBER. So I'll up-level this discussion and say that, okay, so what do we know? We know that we are going to get a lot of errors, right? What do we do if we get a lot of errors? Today in PCI Express, up until before Gen 6, you get an error which was once in 10 to the power 12 bits, which is almost like once in a blue moon. If you get an error, there is a CRC, you detect the error, you ask for the link partner to replay, saying, hey, you send me that packet number 10, that doesn't look good, can you send from 10 onwards, right? So, and it will replay and off you go. With these many errors, if you start asking for a replay, you're going to waste a lot of bandwidth because you're going to constantly be asking a link partner to send errors, to send you replay messages. So we need to have some form of forward error correction. And so for that, we did a little study here. We assumed a 256 byte transfer, and we said that if we could correct always any single FBER instance, what would things look like? What will be the probability of asking us for a replay? If we corrected 2 instances of that, what would the probability of a replay be? If we did 3, what would it be? And of course, there are bigger numbers we tried, but it doesn't matter. The point, I'll make the point even with 3 of these, right? And what you see here is that this is the FBER, the raw FBER rate, 10 to the power minus 4, minus 5, minus 6. What you notice is that even a single instance of correction gets you to a very reasonable replay rate, somewhere around 10 to the power minus 6 or so, but if you are going to get a 10 to the power minus 6 FBER. But notice that the same one with 10 to the power minus 4, your replay probability is somewhere around 10 to the power minus 2 or minus 3, which is a pretty unacceptable number. So what we said is, we are going to go aggressive, go for this point, and then just pick a single symbol correct ECC, FEC mechanism. Why is that? Because a single symbol correct, and then we are going to back it, and then of course we are going to have a very strong CRC because we want to make sure that nothing gets past that CRC. So correction is, let me see if I have this. Oh, okay, no. So correction consists of two things, right? One of them is, of course, your FEC will correct some, not all, but it corrects reasonable enough. Then you got CRC that will detect the rest, right? It has to really be good at detecting. Once you detect, then you can ask for a replay, right? So you got two ways of correcting things. The replay mechanism already existed. Now we are adding to it the FEC mechanism. Now, why do I want a single symbol correct FEC? The reason is that error correction, it's an exponential problem. So if you think about what does it take to correct an error, if you have n number of symbols and you can correct, let's say, up to x symbols, how many permutations do you have? You got n choose x permutations, which in itself is an exponential thing. Within each of those x symbols, you got 2 to the power x possibility, because bit errors can happen, one bit here, one bit there, that way, right? If you look into any symbol, so you got 2 to the power 8 possibilities if you assume your symbol is 8 bits, right? Well, actually, technically, we'll argue 2 to the power 8 minus 1. I'm just making, trying to make it easy. So every symbol can have 2 to the power 8 possible ways in which errors can happen, and there are x symbols, so to the power x. So not only do you have n choose x, you got 2 to the power 8 to the power x. There are that many error possibilities that you're dealing with if you know that there are x errors. If it is x minus 1, you can add that and you can keep doing that math, right? And that's a very difficult thing, and that's the reason why all of those other standards, they pay such a huge penalty in terms of latency. It's because that problem is an exponential problem. And what do we know with one? It becomes linear. So that's the reason why we want to stick to single symbol correct, as long as it's putting me in the right ballpark that I don't have to replay that often. CRC, I wanted a very strong CRC, but what do we know about CRC? CRC is a linear problem. And by that, what I mean is that I generate the syndrome. It's a division thing, fine. I've been doing CRC, which is a division. No problem, we all know how to do that. But at the end, how do I know something is correct or wrong? All that I look for is it 0 or is it non-zero? I'm not trying to look at that syndrome and trying to figure out, hey, which of these n choose x, 2 to the power 8 to the power x is wrong. I don't care. All that I know is something is not right. If something is not right, I just ask for a replay, right? So, lightweight FEC, but very strong CRC. And a maniacal focus on keeping latency low. That's the key. Those are the key things, right, that PCI Express has. And again, that's critical because of the nature of the load store memory-based kind of interconnect that PCI Express as well as similar load store interconnect protocols are. So, now what do we do when we have a forward error correction? Forward error correction works on a fixed number of bytes. I can't have, well, I suppose I can have variable bytes, but that makes my life even more difficult, right? So if I have a fixed number of bytes on which, this one seems to be on a time-based thing somehow. Okay, so if I have a fixed number of bytes, then I need to be able to correct which means that I need to fix that as the unit on which the FEC works. So we define something called Flit, and Flit is nothing new for, while it's new for PCI Express, it's nothing new, right? All the coherent links have used Flit for ages. So the FEC works on that Flit, and we chose 256 byte as the Flit size. So if the error correction is happening at the Flit level, which means that naturally I want to do my CRC during the time when I do the correct. Otherwise, it just becomes more complicated, right? You do FEC somewhere. As far as CRC is concerned, you belong to 5 or 6 different groups, right? So if you do FEC, it makes sense that you do the CRC check. If you do the CRC check, it makes sense that you replay at the Flit level as opposed to replaying at the packet level, transaction layer packet level that PCI Express did. So that's basically where we went, right? And lower data rates will also use the same Flit because you can move between data rates dynamically, so you cannot be having one type of replay if you are in PCI 64 gig data rate and then another type when you dynamically change to, let's say, 2.5 gig data rate. So it's, once you have negotiated, it's always the same way for, again, simplicity. So we picked the Flit size as 256 bytes as shown in the picture here. 236 of these bytes. So we'll see 0 through 235. These are what are known as TLPs, or transaction layer packets. That's what is reserved for TLPs. 6 bytes are for data link layer payload. Then you will see there are 8 bytes of CRC that covers the rest. And then you will see that there are 6 bytes of ECC. Actually, those 6 bytes of ECC are 3 groups of 2 bytes of ECC each. And what happens is that you will notice that those 3 groups are these 3 colors. So what happens with those 3 colors is that each of them is a separate ECC group. So you will see that even if there is an error happening that goes across them, as long as it is less than 24 bits or 3 symbols long, 3 bytes long, that burst, you are going to be able to correct that error. So that's the all right. So that's the reason why we have done arrangement in that particular way. And in the process, what we are able to do is that we removed the sync header, we removed all the framing token, because everybody has a particular slot mechanism where the TLPs go in a particular place, DLLPs go in a particular place. So there is no need to say, hey, this is a TLP type, this is a DLLP type, the locations are fixed. So we are going to get those benefits, as you will see, and no per TLP and DLLP CRC. So yes, we are spending a lot more, 8 bytes of CRC, which is a lot, but that's for a good reason, very strong detection. And we'll see that these help actually in terms of the bandwidth. So even though we are paying more, but because we are amortizing it across an entire 256 byte fleet, we really come out ahead. So what does the retry probability and all of those fit and everything else look like? Remember, my FBAR rate is 10 to the power minus 6. I'm assuming my retry time to be 200 nanosecond, which is reasonably, actually we expect the retry to be less than that, but it's, even if it is 300, let's say if it increases, these numbers don't change much. So the retry probability of a given flit is around 10 to the power minus 6. So what it means is that every 10 to the power 6 or so, right? Every million, I think that's the unit, right? Every million or so 256 byte flit, one of them will get retried, which is a reasonable amount. You have the retry probability over the, if you did like go back n kind of mechanism, that's the retry probability over the retry time. And this is the failure in time. You will see that it's about 10 to the power minus 10, which is as close to 0 as you can get, which is pretty good, right? Anything less than 10 to the power minus 3 is pretty good. And this is at 10 to the power minus 10. And we also did the bandwidth loss mitigation by only retrying the flit that has an error, as opposed to the go back n mechanism. Go back n mechanism already exists, which means that if you got something that is wrong in let's say flit number 10, then you're going to ask for 10, 11, 12, 13, so on and so forth. Everything will start from 10. The other ones just says that just give me 10. I have got 12, 13, 14, 15. I will take it from my local thing, and then after that you can go back to 16. So now let's look into what does this do from a bandwidth perspective, right? Remember, we are paying all of this overhead in terms of the FEC, much bigger CRC and all of that. So what we did was that we put the picture. I think if every time let me not use this and save. Okay, so if we look at this picture, we change the data payload size here in D words. Every D word is 4 bytes. So you'll see that smaller payloads, they get about more than 3x improvement. So remember, because we doubled it, we are expecting a 2x improvement. So why are we getting a 3x improvement? It's because of that efficiency gain. We are not paying the per TLP framing token per TLP CRC, and you can expect to see that will be much more pronounced when the payload is smaller. When the packets are smaller, the overheads are bigger, because you got rid of those per TLP overheads. Those don't matter anymore that much, right? I wonder what's going on. Okay. Huh? Yeah. I know, it's telling me to keep moving. That's a good one. Okay. So, what happened? All right, hot plug, anybody? So, while it's doing something, no. All right. Okay. So while it's doing that, so that's the reason why you will see that most of the cases we have, there is a there is a higher than 2x improvement in the bandwidth, realizable bandwidth, right? And it does taper down. By the time your max payload size is above 512 bytes, you start seeing a bandwidth decline, meaning your bandwidth, instead of doubling the bandwidth, you start getting to like 1.95x kind of bandwidth number, which is not quite at 1.98, it's worse than that. But we looked at it, we said, okay, this is a reasonable trade-off to make, right? Especially given that some payloads you're getting a lot better, some you're getting slightly worse, which is fine, right? We can live with that. So up to 512 bytes, efficiency is better, and beyond that, it's thank you. So then the question is, what about the latency? The table here shows the latency impact that we have for the different payload sizes and all. And the thing to note here is, if it is plus, that means with 6.0 you're going to get that much higher latency, and if it is minus, that means you're going to get lower latency. And why is that? Because you're moving data fast across a faster link, so you're gaining some amount in terms of the latency, right? Because you're running it faster, but on the other hand, you're doing all of these flit accumulation, which you didn't have to do, and that's the reason why you will see that smaller payloads, the latency impact, and narrower links, the latency impact is higher, because you can't really wait for the first D word, which is the 4 bytes of data, and say, hey, I got my 4 bytes of data, let me go and consume it, which you could do in the previous case. Here you have to wait till the 256 boundary. So we take all of that into account, and you will see that overall these are by 1, but if you look into the by 16 kind of number, it's a vast, you start gaining the thing. And I didn't even credit us for the latency savings due to removing sync header. Basically, you get rid of a bunch of muxes, all of those things. So if you take those into account, mostly you are going to come out ahead. So how well did we do compared to the So how well did we do compared to what we said, right? Data rate, of course, we met the data rate. Latency, we exceeded the expectations, right? There are a couple of cases where we didn't quite meet, but that's fine, that's reasonable. Bandwidth, again, we generally exceeded the expectation. Reliability is pretty good. Channel reach is the same. Power efficiency, of course, your mileage varies. And then for low power, we introduced a new L0P state, which will get us real power savings and fully backward compatible, and then HVM ready, right? So pretty good from all of that perspective, and expect the same with PCIe 7.0. So then the question is, okay, what about storage, right? So one of the key drivers for PCI Express has been all the SSDs, right? So if you look into, and in general, the thinking is that, hey, SSDs they're not at the bleeding edge of technology transition. And I used to think that myself, right? Generally you expect the GPUs or the networking guys to be at the bleeding edge of the technology transition. Storage generally will follow a year or so later. Been proven wrong, and this is one of those things where you're happy that you're proven wrong. So If you look into PCI 5.0 integrators list, right, we did the compliance program. The very first set of devices that got qualified are SSDs. So aggregate bandwidth consumer, but at the same time, pretty much moving at the leading edge of the technology transition. And it's all, especially with NVMe, latency is lower. With hundreds of lanes coming out of the CPU, you are no longer going through a different bus converter kind of thing. You're directly sitting on the CPU bus, very low latency access, and to the point where right now the storage stack is not really the bottleneck, right? And that's putting a lot of pressure on the networking side to catch up, and which is good. That's the way we want that entire virtuous cycle of innovation to happen, right? We don't want storage to be slowing things down. And these are the, again, some of the recent data in terms of how many devices are connected to PCIe, and the green one is PCIe. So you can see that, which is a good thing. Same thing by capacity. The dark, different color here. This color is PCI Express, so pretty decent there. And PCI Express has got a lot of sorry, I apologize for this. Now, it's some combination of, it's trying to also increase the font size, which is, okay. So PCI Express has got pretty good RAS capability, right? I mean, we have all of our, as you saw, right? We take our reliability fairly seriously. We have error injection mechanism defined. We got hierarchical timeout support for transactions, right? So, and also containment that we will see, and advanced error reporting, support for hot plug, planned hot plug, surprise hot plug. So, and especially for the storage segment, we did the notion of downstream port containment, which basically says that, hey, as you move from this HBA kind of topology to a direct PCI Express connect, you want to be, people always plug out the wrong SSD, and you need to make sure that, you're not bringing down the whole system. So we defined the containment such that the containment is limited to the device that is being impacted. All the other devices will continue as usual, even though they're under a switch hierarchy, right? So what you want to do is that, if you're under a switch, you don't want the CPU's root port to be timing out on the other SSDs that are not really impacted, right? So those are the types of things that PCI Express did to address those issues. IO virtualization, again, it has been there for a long time. We support IO virtualization natively in terms of having a lot of the virtual machines access to the virtual functions of the devices. And again, storage was one of the early movers along with networking to the virtualization space. And we are also working with DMTF to define a lot of security mechanisms so that it's we basically want to have a very coherent strategy, right, in terms across different types of IOs, in terms of the security solutions that we offer. So we take advantage of a lot of the work that DMTF has done. We define a set of protocols on PCI-SIG. As you can see, this is basically the split of what PCI-SIG did versus what we are leveraging from the MCTP, DMTF stuff. So all of those are fundamentally what you're trying to do is that you're trying to make sure that you're authenticating the device on the other side, and also any traffic that is going across PCI Express is protected with encryption, both end-to-end encryption and or per hop encryption, right? So that's basically where we are at. PCI Express, again, one specification, same silicon, but multiple form factors. Again, if you go for, the form factor that you expect in here is going to be very different than that of a server, right? So it makes sense that one specification, but multiple form factors, and these are, a whole host of them, right, that you can see. Some of them are done by PCI-SIG directly. Some of them are done by, other organizations such as yours. So all good stuff, right? We're also working on the Uh, yeah, they're trying to send me a message. So we're also trying to work on the cable topology. And this is an interesting development actually. So, there are internal cables and external cables, and of course, they help us with respect to the reach. But most importantly, there is a move so far, right? PCI Express and any kind of direct load store interconnect was based on a given node. In other words, if you have a system, if you have a server, right, and you put a GPU or you put a piece of memory there, it's captive resources for that server. Any kind of DMA or anything is within that server, right? In other words, if I have a rack of servers like you can see here, right, and let's say if you need the storage somewhere else, or if you need the memory from some other node, there is no way for you to really do that other than go through some kind of networking semantics, right? And we are moving towards a world where load store will access those directly. So what we mean by that is that you want to be able to have your pool of resources that you are going to be able to access using the load store semantics, such as whether it is PCI Express, whether it is CXL. So that way, you can imagine that in the future, you can have some nodes that are going to have some amount of, let's say, SSDs, some amount of GPUs and all of that. And then, you can have some of the others in a pool, so to speak, right? And we have hot plug flows. So we can remove, let's say, a GPU from the pool, assign it to some server. And then once it is done, we can basically remove it, put it back in the pool, and then reassign it to somebody else. So, and in order to do that, you will need some kind of cable topology. So, we are working on in terms of the cable topologies to realize that vision going forward, right? And there are other things that we are working on, like unordered IO and things like that, which is basically going to fundamentally PCI Express is like CXL and other these load store topologies are moving towards more like a fabric kind of thing. It's a gradual shift, but it's a very strategic shift that's happening, right? So something to keep an eye out for, right? So clearly the normal mode of load store and everything, the frequency doubling, everything continues, but in addition to that, we are having those. Any successful, as we all know, any successful standard needs to have a well-defined, robust compliance program, because if you have, parts that are out there for 2 decades, and you got a 900-member company consortium developing technologies that are based on a standard, right? How do you make sure that they all interoperate with each other, right? And one of the means to do that is to come to a compliance workshop and get your part tested for compliance, right? So we have got an extensive compliance test suite that covers everything from electrical signaling to link layer, are you doing the replace properly or not, to the transaction layer, to the configuration register. So it's a fairly well-defined compliance mechanism that we go through, right, in the compliance test suite. And the other thing that it does is it basically brings in that mindset that specifications, right, are well-defined, that somebody can design to without knowing which other component it's going to interoperate with, right? You're all going by the setup standard, and then you can't really possibly pick up the phone and as a designer and talk to every other designer that would have worked across any other company, right, and expect to make it work, right? And this is basically our means of enforcing that compliance mechanism through the compliance workshops. So in conclusion, right, PCI Express, we got a single standard that covers the entire compute continuum. It's a predominant direct IO interconnect, right, from the CPU with high bandwidth and used for alternate protocols with coherency and memory semantics, low power, high performance. And I used to, generally I say to people that PCI stands for peripheral component interconnect. It definitely is a peripheral component interconnect, but also now it's the main component interconnect, right? It's moved from the periphery to the main part, and then also it's moving beyond the periphery into the rack level, right? So which is the goodness of it currently on the 7th generation, and again, expect to see the innovation engine to continue, right? We got lots of very interesting and real problems, right, that we want to solve, and the journey doesn't stop, right? It's going to continue. So with that, open to questions if you have any. Yes.
Yeah, so channel reach, you're looking at one SI and the interconnecting system. As far as the channel, Gen 5 was a big step up in the system design.
Mm-hmm.
So there's really, how much burden is there possibly going into Gen 6, especially the cost of or is it truly where is it at?
So as you know, right, I mean, we try to, a lot of the, it's a shared burden system, right? It's like, a lot of it goes to the silicon side, and then there is, of course, you do expect things like, we are expecting the materials, right, the low loss materials to become, which has been the case, by the way, right? We've worked on this for a long time, but things have, the loss per inch in terms of dB, right, for a given frequency has gone down, right? And that's because these are all volume platforms, right? So Jonathan, as you know, this is like the volume economics is at play, right? If the demand is there, somebody will do it, and it's not like people are just like we know how to do things in this, as we in this context is PCI Express to do the technology. People that are making the materials, they know how to do the lower loss. It's a question of when do they become more mainstream volume, right? So there is that material cost that you brought up, right, which is basically on the board side that adds to the cost. And then also, even on the connector side, right, there are a lot of innovations that have gone on, right, in terms of making sure that the loss there is, you're basically, there were discontinuities that we made sure you're pretty much, I feel like every generation we are pushing it out, that huge upswing of that curve, and we dodge the bullet, and we will keep pushing it out, right? We'll come up with something and we'll push those out, right? There will always be those discontinuities. And then the other thing is, of course, backdrill and all of those things that we have been doing. And most importantly, it's on the package side also, right? Lots of innovations happening to mitigate the package loss there, right? So it's a combination of all of those that we really have to together work with, right? And again, as I say, right, the ones that really, that thing that really helps us is the huge volume in which we get deployed, right? I mean, that makes it possible, right? Otherwise, it just becomes a boutique technology. Right, so hope I answered that question.
Yeah, so some of the exotic materials that are more expensive become less exotic, less expensive.
Exactly, yes, yeah. Yeah.
But in a data center world where devices never sleep or should not sleep because they need to use 99% of the time, do you have any comparison between what would be the per transceiver power increase from Gen 5, which is energy based, to Gen 6, which is time based?
Yeah. Okay, so I think there were two questions. Let me answer both one by one. So the first one had to do with the devices should never sleep, and yes, L0P is when the devices are not sleeping, right? So what the basic premise there is, if you have a by 16 link, for example, let's say you are monitoring how much bandwidth you are consuming, and you say, hey, I've been consuming less than 25% of the bandwidth. So you bring it down to 4 lanes. 12 lanes go to sleep. They go to the low power state. The other 4 lanes are active. Under L0P, at least 1 lane is always active. So in other words, any transition, right, at no point your link is out of commission, so to speak. In other words, you are able to do transactions all the time. Even when you're trying to bring up that by 4 link, let's say 25%, let's say you saw that, hey, my utilization is now at 25, maybe my queues are backing up, let me get to from by 4 to a by 8, right? So you upsized your link to a by 8, right? While you're upsizing, 4 lanes are training, but these 4 lanes that were running, they will continue to run your traffic. The other 4 lanes will train in the background. Once they're up, we will seamlessly bring them in. And there is a point called skip order set is then we send periodically. During that time, we are going to upsize the link to a by 8. You will not know the difference, okay? So that's first part of the question, right?
Key thing is no more stalls.
No more stalls. And this is one of those learnings, right? That you go through, you make mistakes and you learn, right? That had to do with the dynamic link with for those of you that and when we saw that, why is that not getting deployed? Like, oh yes, of course, stalls are bad, right? The second part is power efficiency numbers, right? And your mileage generally varies. So in general, right, what we have seen is anytime there is a transition, people typically will start off with about 1.5x or 1.3x of where they were the previous generation, which is not a 2x, but it's not going to be half. Meaning it's not going to be 1, right? So they will meaning if you do picojoule per bit, they will be at around somewhere around 0.75, whatever, that kind of a number, right? I mean, they're not going to be at half. Over a few generations after they do the design, in general, they tend to go down. Does it mean that you're going to keep, as you're doubling the data rate every single generation, your power efficiency number will asymptotically go to 0? No, but we have been pretty good in terms of it's amazing when people get a budget what they will do or what they can do, right? So any other questions? Yes.
Talk a little bit about L0P, and since it's a storage conference, how L0P might work with NVMe.
Yeah, so L0P, the way it works is you can have any application running on top. Doesn't matter, right? It can be NVMe, it can be your whatever GPU, doesn't matter. The hardware will be monitoring how much bandwidth consumption is taking place realistically on this link, and we can know that because we know when we stuff idles. When we don't have transactions to send, we send idle. So it's very easy for hardware to monitor at the most lowest level. You can do a very quick calculation, and you can have different policies. You can say, hey, if I see that I'm going to take an average over the last 10 microseconds, let's say, and if I see that I'm consistently using the link less than 25% of its utilization of the bandwidth that is available, maybe I go to a by 4. Or if I'm a little bit more, especially for NVMe, you can, you don't have to move back and forth that fast, right? We also have mechanisms where the other side will tell you that, hey, how quickly can I go from a by 4 to, let's say, a by 8, realistically, right? I mean, remember, there is no stall. The 4 lanes will run, but the other 4, how long will it take for it to really come back up? So every design is different, so that gets exchanged, right? So you can make a policy based on that hardware policy, saying, how quickly does it need to turn, right? In reality, it's like, microsecond kind of number, right? So think of it as if I monitor the traffic for a microsecond or 2 microseconds, decide to switch it back or forth, then anything to undo that, right? Especially on the upsizing part, it will take me 1 to 2 microseconds. That's a reasonable thing for me to do, and I'm going to save the power. Your block read will not.
And then a microsecond later, it might go by 2, and then a microsecond later, it might go by 4, and it'll just keep ticking up in performance. So you'll see this kind of.
Actually, you will see, if I see that reads are easy because reads I know if I want to, I can look at the reads and know that there is a huge bandwidth demand coming. So I could easily, I can have some intelligence to predict that. Writes might be a little bit more tricky, but nevertheless, so even if you have a write, I can always look into, how far my hardware queues are getting backed up, right? And based on that, I can decide saying, hey, these things are coming in fast, right? The build-up is really fast, so instead of taking small steps, I might just decide to go all the way to by 16 and then dial it down later on. So you could have different policies depending on how, you can look at the slope at which things are building up, and based on that, you can make a decision.
Right now, all of that work is planned to be on the PCIe side of the device.
It's all on the hardware side.
Side of the protocol. We're not planning on making changes. I'm aware of them.
No, you don't need to make any changes in the upper layer. Yeah.
So you said, I don't know, increasing number from the worst slide deck, it said 128 lanes. So this L0P doesn't create some soft distribution of lanes. If I have a 4-lane device, I have a 4-lane device.
You have a 4-lane device.
He is only using maybe 1 right now or something like that.
Oh, Oh yeah, if you have a 4-lane device, you're going to have a 4-lane device. Now within that 4-lane device, you got choices. You can just say, hey, I always want to be 4 lanes. To hell with your power story, right? Which is fine. You will always be 4 lanes. I could make a request saying, hey, we are using less than 25%. Can we go to by 1? You can always say, forget it. I want it to be by 4. These are opportunities. No. Those are all independent things. Yes. Yeah. These are all, at the end of the day, you want to, just like any low power state transition, right? It doesn't take away from your max, from the capacity that you had planned. What you're doing is that you're looking at the current consumption and say that, hey, do I need to keep this consumption rate going? Or can I dial it down temporarily and then when I need, I can flip it back up? But your by 4 will always be by 4. It will always deliver you the by 4 worth of bandwidth. That doesn't go away with L0P. All right, if you have more questions, I'll be here. I was getting the time up indication, so thank you all very much.